Control click. Yeah. So this contour integral here, that basically just means as you go around, times the speed by the distance you go around, and add that all up as you go around. So the notation there is kind of calculus notation, which we'll come on to later on. But this basically accounts for the fact that maybe the velocity of the particle might speed up or slow down as it goes around. Okay, so it's not maybe always going at a constant velocity. So we can account for that by using calculus. And then the vorticity, which is the amount of circulation per unit area. So if something is very big and circulating very slowly, that's got maybe the same vorticity as something that's very small and rotating very quickly. And what we see when we do this kind of experiment here is that when we start it kind of going, the water gets drawn downwards, okay, through the hole, which means it gets stretched. And that's basically turning a fat thing into a long, thin thing, which means the area of circulation is getting smaller. Okay, so vorticity is circulation divided by area. And if the circulation stays constant, that means the vorticity must go up. And that kind of is explained in this maths down here, which is basically saying if you keep one thing constant on the bottom of a fraction, on the top of a fraction, you change the thing on the bottom of the fraction, then the answer will change correspondingly. So then I asked this series of questions. So imagine the square-sided sink. To calculate what the circulation is in this sink. So basically, we've got 0.5 by 0.5 kind of sink meters. The velocity is 0.1 meters per second. So the total kind of perimeter of the sink is 2 meters. Okay, and if we add up the velocity as we go round, so we times the velocity by the distance, we will get 2 times 0.1. So that's what C equals, the circulation. And then if we wanted to work out the relative vorticity, so that's the vorticity due to the local thing, that's circulation divided by area. And that's the area of that is 0.5 squared. Okay? So, did anybody work out what that was? As a number?
Yeah, but it's wrong.
What do you mean it's wrong?
Well, I didn't do that.
Oh, right, okay. So you worked out a number, but you didn't get...
Yeah.
Okay, well that's fair enough. So actually, this is one of the important things about this course, is you don't get all of the marks for getting the right answer. Okay? We're very much interested in how you get to that answer. So you get marks for showing what you've done. Okay? So if you just write down the number at the end, you won't get enough marks to pass the course. So always show all of your working. Always write down the units. So that's another important thing that we kind of checking. And always write your answers down to the correct number of significant figures, if that is appropriate. Sometimes you've got an absolute number. That's your answer, and sometimes it's a series of measurements, so there will be an accuracy with those measurements you need to consider. But so just to kind of work this through, 2 times 0.01 is 0.02. Okay, a half squared is 0.25. Okay, half of a half. And then, sorry. So you could whack that into the calculator if you wanted to, but you could also think about that. If this is 0.25 is a quarter, so that's the same as saying 0.02 divided by a quarter, which is the same as saying 4 times 0.02. Okay? So we've actually got 0.08. Okay? Don't get the right answer for that because it's in seconds to the minus 1. If you work through your units, okay, we've taken a length times a speed, so that will be meters squared per second, and we've divided it by meters squared, so the meters squared cancel out, and we just get per second. So again, we have to have the units in there. And we could write this out as scientific notation, which we're going to come on to later on in this lecture. So we could write that as 8 times 10 to the minus 2 seconds to the minus 1. So hopefully you can see here that actually the planetary vorticity, so this is the spin due to the rotation of the Earth, that is almost 100 times smaller than this. So what this means is that the Coriolis force does not determine, is not relevant for water spiralling around in your sink.
So it's the less important.
Yeah, it's the less important. It's a smaller number. Yeah. So so we can say that the Coriolis force doesn't matter. But one of the really useful things about doing maths like this is this now gives us a tool that we can use to maybe design a new experiment. So we could ask ourselves, well, actually, if I make my sink bigger, if I wanted to demonstrate the Coriolis force, how big would I need to make the sink for the planetary rotation to matter? So how big do I need to make this number? Okay, if I made that 1 meter by 1 meter, okay, then 1 squared is 1. Yeah? And so now my relative vorticity is now only going to be 0.02, 0.02, or 2 times 10 to the minus 2. So the relative vorticity is now smaller because I've made the sink bigger for any same speed of water moving around. It's still not, okay, it's still not smaller than the planetary. Okay? So what I could do is say, how big do I have to make it to make my relative vorticity the same size as the planetary vorticity? So in this case, what could I do when if I said that, how do we draw this? Squiggle, which is zeta, I think, which is kind of round. So that's the relative vorticity. When does that equal the planetary vorticity? Okay. So you can see now I'm able to do things with this maths. So I could then set this equation to be 1.2 times 10 to the minus 4. When does that equal our speed? Which will be, well, actually, sorry, I didn't change this here. So if that's 1 meter, 1 meter 1, that'd be 4. So this would end up being 4. Still smaller. Okay. Actually, well, I'll set that for you as a kind of like a homework thingy. So here's basically how you can try and answer that last part of that question by setting this. So we've basically now got an equation. When does F equal C over A? Okay, where C equals the perimeter times the velocity. Okay, so it's slightly easier to work out what the velocity would have to be, but you can also work out the perimeter, because this area is the perimeter divided by 4 squared. So have a think about how you're going to go around doing that. Anyway, so we're going to talk a little bit now about this scientific method. All right, rubbing this off, you're busy.
Yeah, it's fine.
Cool. So I injured my shoulder mountain biking. It really hurts. So don't do that. So this idea that Massimo kind of mentioned briefly yesterday, basically we come up with some hypothesis, we test it with some data, and then we see if it agrees or not. So basically, maths comes in two places in this, in terms of the forming the hypothesis, basically making some model, usually based on maths, and then also testing the data. So if we make some measurements, do they agree? Is this number the same as that number? And that, we'll come on to that when we come to the statistics part of this course. But before we go on to the model part of, or this scientific method, I thought this is like the most basic it can get. And this is also one of the hardest parts of maths and science, is figuring out from a question that's written out in words what kind of maths you're going to have to do. Okay? So in this case, we've got some information that's written out in words, and then you've got to think about what kind of maths are going to help me solve that problem. Okay? And it's very hard to give you kind of like a set of rules to follow that will enable you to figure out what maths to do. Okay, so this kind of skill only really comes with extensive practice, by doing lots of these kind of problems and thinking about it, and particularly going to the tutorial sessions where you can actually talk through the process with some of the demonstrators. But briefly here, annoyingly, this example uses pen and paper, two things that begin with P. So substituting in letters for those in algebra is a bit tedious. I'm just going to say that the cost of pen is equal to E, because that's the second letter, that's cost. And the cost of paper equals A. So one of the things that's quite helpful to do is to try and write out the information that you've got as an equation. So I know from the first thing, I guess we anybody, any rough, who thinks, the paper cost £1? Anybody happy with that? Cost £1? No? Yeah. Okay, right. We're all happy that the paper costs £1. Okay, everyone thinks paper costs £1. Okay, put that in the ideas fridge and snack on it later. Okay, so we've now got some equations, so we can write, so the pen plus the paper equals 1.1. Yeah, I'll just get rid of the pound symbol because that's just going to be tedious. All units now in pounds. And we've got a second piece of information. We've got the pen. Okay, the cost of the pen is equal to 1 plus the cost of the paper. Yeah? Happy now? So what we've got here is two equations, okay, and we've got two things that we don't know. So it's quite often a nice check before you start kind of off onto your route of doing lots of calculations, is just to check if the problem is solvable. And one of the kind of general rules of this kind of thing is that if you have two things that you don't know, you need to have two equations. Okay? Now you can't have one equation and just rearrange it. Okay, so I've got two equations. It's the same equation, just rearranged. So you can't rearrange one into the other. Okay, so they are two independent equations that have at least one of the variables in each of them and have both of the variables in both of them, if that makes sense. So what we can do now is, now we've got two equations, we can use our maths tools, and there are lots of ways or routes to solve this. But one thing you can do is you can rearrange, or you can, one of the equations to isolate one variable on one side. We don't need to do that here, because you've got an equation that says E equals something. Okay. So I can then substitute into this first equation. So if this is 1 and this is 2, I would say I'm substituting in 2 into 1. Sometimes circles around those to making sure that we're labelling things rather than just they're not numbers. In this case, I would write 1 plus A. I could put brackets around that. Good practice, doesn't matter in this case. Plus A equals 1.1. Okay. So now I've got one equation that only has one of the variables in. Okay, so I can solve that equation and then use that to work out the answer. So I could multiply, this is the same as writing 1 times 1 plus 1 times a, which is just 1 plus a. So in this case I've got 1 plus a equals 1. Happy times. That's just 2a. Well, a plus a is 2a, so I've now got 1 plus 2a equals 1.1. I'm just going to move up around the head on the side. I could take 1 from both sides. So when you're manipulating equations like this, if you're simplifying things, you don't need to worry about the other side. But if you're adding, subtracting, multiplying, then you need to do both sides of the equation. Otherwise, errors occur. So in this case, I'm going to take 1 from both sides, so that just becomes 1 plus 2a minus 1 is just 2a. So 2a equals 1.1 minus 1 is 0.1. And then, to get rid of that 2, I'm going to divide by both sides by 2. So this becomes a is equal to 0.05 pounds. That tells me the paper is 5 pence, and I know that the difference between them is 1. So the pen is £1.05. So, bit wrong. It is also worth, when you come up with an answer, checking is it vaguely correct. Okay, so we all thought it would be about 1. Okay, 1.05 is about 1. If we came up with an answer of 100 million, which is not the most ridiculous answer I've ever had in an exam, then you'd go, that's probably not right. Okay? And even if you can't figure out why it's not right, write down, this is an unreasonable value. Because this at least shows your examiner that you're thinking. Okay? Not all examiners would give you credit for that, but I would. Right, so let's get on to the scientific method. So this is an article that appeared. I'm okay rubbing?
Yeah.
With the good arm. This is a news article that came out a couple of years ago about speed limits in Edinburgh. Okay, so they're introducing this 20-mile-an-hour speed limit. It's been rolled out over much of Edinburgh already. So when this came out, one of the lecturers, I'm not going to say which one in this department, but one of them wrote this Facebook post, which was basically moaning about his brother. I think is going to take his 1 hour journey into work is now going to take 1.5 hours, and this was terrible. Okay, so we can now go through the line of thinking that this lecturer has gone through. Okay. So we've changed the speed limit from 30 miles an hour to 20 miles an hour. So he's used, he or she, anonymous lecturer, it's a he, a model. Okay, and he's used this model. The model they've used is speed equals distance divided by time. Pretty standard stuff. He's rearranged that model to give himself time. Time takes to work is the distance from his brother's house to his brother's place of work, brother or sister, divided by the speed. Okay. Now he doesn't need to know how far away his brother is, because you could basically, the old time it took to go to work is the distance divided by the old speed, and the new time it's going to take to work is the same distance. Okay. The speed limit hasn't caused the house to move further away, divided by the new speed. So we don't need to know the distance. We could, so the distance is equal to both of those things in those versions of the equation. So the new time, okay, we can just basically, because the distance is the same, we can then just take, so we can just, because the distance equals the old time divided by the old speed, it also equals the new time times the new speed. So we can just ignore this bit and just use this part of this equation here and rearrange that to figure out the new time. Okay, which is just this times this divided by the new speed, which is what we've got there. So the prediction that they have made that the 1 hour journey takes 1.5 hours. That seems pretty standard, pretty sensible so far. So we've gone through this process of forming, there's a problem, his brother's late for work, this kind of stuff. He's formed this hypothesis, used the model, okay, and the model has come up with a prediction. And now what we do is we then see if that agrees with reality. So, some people didn't like stalk his brother around and time his journey to work, but they did some experiments by basically doing a survey of bus times and working out what they would be if the bus was limited to certain speeds. And it turns out that it would only take 2.5 minutes longer, this hour-long journey, if you change the speed limit. Right? So this doesn't agree with this model. And hopefully, I think you all know what's wrong with the model. Okay, anybody want to say what might be wrong with our simple model?
Traffic.
Yeah.
Traffic? So what do you mean by traffic? What's the, I guess the...
Well, cars could be moving at 15 miles an hour the whole time.
Yeah.
So,
Not constant speed.
Yeah?
The traffic light, the way they kind of change, like.
Yeah, so this idea that the speed limit is limiting the speed of the vehicle, it's a bus, right, which stops all the time. So even if there was no traffic at all, it wouldn't be at its maximum speed all of the time. And it's definitely not at its maximum speed all the time when there's traffic. So there's only a small portion of the journey where the bus would be, if the speed limit was 30 miles an hour, would be in between 20 miles an hour and 30 miles an hour. And that's the only change in the journey, time. Okay? So we then need to go back and make a new model that's more complex, that includes accelerations and decelerations, amounts of traffic perhaps. So it doesn't matter really how much longer it'll take. And also this doesn't account that if we have a slower speed limit, more people might ride their bikes or walk to work. And then there'll be less congestion, so maybe the bus will go faster. Okay, so there's always you can always make a more complicated model if you have the time on your hands. Okay, so what we're going to be doing, I guess, for the rest of this lecture is starting to go through some of the maths parts. We've done some examples first. We're going to go on to do some maths. So the first bit, of course, will be about subscripts and superscripts. So these are and symbols. So quite a lot of the time we're going to be using Greek symbols to replace numbers or parameters, just like in the vorticity thingy. Zeta is the local vorticity. Don't worry about knowing all of these things. It doesn't really matter. You could quite often just put a smiley face or sad face instead of them. We're just substituting a parameter or a number for one of these things. It just makes scientists look a little bit more inaccessible. Some of them are worth, I guess, knowing. Those things like theta. So that's so this one, theta, is quite often used to measure angles. Some of them are specific numbers. So pi is the circle constant. Lambda is quite often used for decay constants. Omega is sometimes related to wavelength or rotational velocities. And delta is quite often a small change used in calculus, which we'll come to later. But quite often these can be, I'll try and introduce them when we get to see them. So the next thing is that sometimes these parameters or numbers have a subscript or a superscript after them. So usually the superscript means something mathematical. It's usually a number or a variable, and that usually means you're timesing that number by itself that number of times. So x squared, x cubed, x to the power of minus a half. Okay. The subscript usually doesn't have any mathematical meaning. Okay. So it has a, sometimes in, if we have a series of numbers, a sequence, it might determine where you are in that sequence. Okay, so the first number in a sequence, the third, fourth, fifth. But it's mostly used in science to tell us something about the variable that we're measuring. So for example, we've got rho here, so it looks like a P, but it's actually the Greek letter R for rho, I guess. But we've got a subscript air, so that's telling us the density of air. So if we had rho water, that might refer to the density of water. So usually subscripts tell us something about the thing that we're looking at, and the superscripts are a mathematical thing. Again, I'll try and remember not to massively confuse you. I've got to say that the superscript, where it's got a mathematical meaning, is sometimes called the exponent, and that just means timesing that variable by itself that number of times. Doesn't have to be a whole number of times, which is kind of a little bit odd kind of concept. So you can times something by itself 4.793 times, which is odd, but you can do it. Okay, so this is kind of the meaning of that. So x squared means x times x. X cubed is x times x times x. Sometimes called the cube, but they don't have to be whole numbers. They don't have to be positive numbers. So they don't even have to be real numbers, but we won't get onto the difference between real and imaginary numbers. So just some of the rules that we have to deal with when we're doing these things. Okay, so if we have a variable x, y, anything, to the power of something, and then if it's times by the same variable. So if it's a different variable, if I had kind of x squared times y cubed, this rule would not apply. It's only if these variables are the same thing. So I'm using dot for times because x times x gets confusing, right? So sometimes sometimes people write these x's with curly, not the Coco Chanel symbol, but kind of like that, two inverted C's, to make it clear that that's x, not times. I'll try and remember to do that, but so this should be x, that's x times x cubed. Okay. So the first rule is that if you're timesing variables together, okay, you just add the exponents together. Okay. So in this case, this would be x to the power of 5. Okay. So just also to point out that just x on its own is the same as x to the power of 1. Okay. So this rule, if I had x times x, that's equal to x squared. Okay, 2x is x squared. And if we look at the exponents on that, that would have been 1 plus 1 plus 2. So the second rule is the dividing rule. If you divide one variable to the power of something by another variable to the power of something, you just take the exponents away. So in this case, if this was divide here, this would be x to the minus 1. Okay? So the thing that's on the, another way of writing this would be x squared over x cubed. Okay? So x to the minus 1, okay, now we've got a negative exponent, so that has another special meaning, so that's timesing it by itself minus 1 times. But another way of writing that is 1 divided by x. Okay, so if this was, this would be x to the minus 2, and then we'd have 1 over x squared. So if you've got a minus exponent, okay, then it just means 1 over that value, or 1 divided by that value. And then the last rule is if we have an exponent raised to the power of an exponent, so that's like saying x squared, kind of, and then to the power of 4 or something like that, or x squared. You just times the exponents together. So in this case, it would be x to the power of 8. Okay? Yeah, so I've already explained the, I guess this one here, when x is times itself 1 times, that's just the same as x. But there's also this quite useful relationship here when if you make x the exponent 0, okay, doesn't matter what x is, what parameter it is at all that's kind of times by itself no times, okay, the answer is always 1, which is kind of a little bit counterintuitive that it's not 0, but it's 1. So that's just something for you to remember. Let's not bother with that because those are. Let's talk about how these things could be useful. So this is a cloud. I guess you might be familiar with them in Scotland. So clouds form when the air has got lots of water in it, okay, but that water's in the gas phase, so you can't really see it. And then if that package of air cools down for some reason, or gets compressed a little bit, maybe, pressure increases, you might condense the water. So in the cloud, it's energetically favourable for the water to be in the liquid phase rather than the solid phase. Okay? So there's some thermodynamics that's basically making it energetically favourable to have water rather than water vapour. And you might form a water droplet. Okay? So if you've got gas, and then you start condensing that, you might get droplets of liquid. So the thing about droplets of liquid is that they have a surface, whereas the gas doesn't have a surface. And particularly with water, and if you kind of do oceanography as an option, you'll find out that water has a very, very high surface tension. Okay? And to have that surface tension costs energy. Okay? You need to effectively put energy into the system to allow the water to have this slightly excited state along the margins of the water drop. So we get some energy into the system because we're condensing water, and we're condensing water vapour and forming water, and that's proportional to the amount of water that we condense, okay, which is related to the volume of the water drop. The volume of the water drop is 4/3 pi r cubed. Whereas the surface area of the water drop, okay, that's costing us energy. So we have to put energy in to form that surface. Okay? And that surface is the surface area of the sphere, which is 4 pi r squared. Okay? So if we're going to grow a water drop, it's going to get bigger, okay? Which means we're going to, basically, energy will be not created but added to the system because we're, or the system will give out energy because we're condensing water, and that's thermodynamically favourable. So we're forming more water, our drop's getting bigger, and the water wants to be in that liquid phase, okay? So the water droplet will be giving up energy. But as the water droplet gets bigger, the surface area gets bigger. Okay? And a bigger surface area means that we've got to put energy into the water drop to form that surface area. So we've now got two, they're not quite equations yet. So the energy of the surface tension of energy of the drop is proportional to, so that kind of like squiggly kind of ribbon type symbol. That just means proportional to. So we could say it was equal to the surface, some constant, so maybe the energy required per unit area of water times the radius squared. Okay? And similarly, the energy from the change of state, okay, so that's coming out of the water droplet, that's giving up energy to the environment, so that's kind of spontaneously happening. That's proportional to the size of the droplet, so proportional to the radius cubed. Okay? So this is all very well and good, but as our water droplet gets bigger, which of these terms is going to be more important? Is it going to be the gain in energy from having more water condense, or is it going to be the loss of energy from having to have more surface area? So the thing here is that as a number gets bigger, if you cube it, if you times it by, so if you go from 10 to 100, okay, then if you cube that number, it's going to be 100 times, it's 10 times bigger, right? So it's going to be 10 times 10 times 10, which is 1,000. Whereas if you only square it, if you times it by itself, it'd be 10 times 10, which is 100. So 1,000 is bigger than 100, right? Okay. But what if your number is actually very small? What if you've got a very, very small water droplet? Okay. So what if your droplet is 0.1? Okay. So 0.1 times 0.1 times 0.1 is 0.0001, right? Which is smaller than if we square the number and go from 0.1 times 0.1, which is 0.1 squared, is equal to 0.4. Whereas cubed, it would be 0.1 times 0.1 times 0.1 cubed, 0.001. Okay? So this is kind of important in clouds. So if we actually look at the energy, okay, that basically comes out of our water droplet, or the energy we have to put into the water droplet, sorry, it's the surface tension energy minus the energy we get from condensation. And when the radius is very small, as we go from a small radius to a slightly bigger radius, this term is bigger than this term. So we have to put energy into the system. But as the droplet gets past some certain size, then if we increase the raindrop size, then this term starts to beat this term. Now the exact point that the size of the raindrop depends on those constants of how much energy per surface area, or what is the enthalpy, the amount of energy we get from condensation. Okay, it doesn't matter what those constants are for this, but you can see that, and actually this is the graph along the bottom here. What I've done is that's the slope of the top graph. So it's how much energy you need to grow the drop a certain amount. And you can see that it's kind of above 0, so our gradient are positive here, until we get to this point here where our gradient starts to be negative. So for a small growth in raindrop size, we actually get energy back because we're in the negative portion of this graph. So going from this graph here to this graph at the bottom, that's basically calculus, going from kind of the shape of a graph to the slope of the shape of a graph. And we'll come on to that at the end of the course. But this basically means that if raindrops are very small, you can't grow them. They will want to be small. Whereas if raindrops are very big, they will spontaneously get bigger and bigger and bigger. Which is a problem, because raindrops have to start out small because you're condensing them from a gas where the water are in clusters of one water molecule, and then you've got to suddenly grow that into a huge cluster of water molecules, otherwise they won't grow any bigger. Okay, so according to this model, clouds shouldn't exist. Right? And we know that they do. Okay, so again, we're going through that scientific method. We're going to say, actually, we need to revise our model. Okay, because clouds exist. We have some clouds outside today. They're very beautiful. So actually, we have a more complex model, and do not worry about this model. This model is not part of this course. So this is if you were to do the meteorology, weather and climate, I think, or meteorology atmosphere. One of the meteorology options in geosciences. But basically what this is saying is it's just our model that we've just done assumes that water condenses out of kind of a gaseous phase into water droplets. It's not what happens. There are a whole bunch of other effects in that there's actually small bits of dust in the atmosphere and water condenses onto those, and because they have a surface, okay, then the volume is not proportional to r cubed, because the water is spread out over the surface. It's actually proportional to r squared, or the square of the volume. So, so actually we can get clouds forming as long as we've got something to nucleate the raindrops on. So if we had a perfectly pristine atmosphere with no dust in it, there might not be any clouds. Unfortunately, we have a dusty atmosphere, which we'll come on to in Evolution of the Living Earth if you're doing that course. If you're not doing that course, don't worry. You'll find out about it sometime. Yeah, so that's the effect of dust. Okay. So I think we're going to stop here. Yeah, we'll stop here because it's no, it's not. No, we're not stopping here. We stop at 1, don't we? Do we stop at 1? Yeah, let's stop at 1. I'll just introduce this concept here. So, because we deal with very large and very small numbers in science, we have a kind of a notation, a way of writing down numbers which helps us do this. And you might be familiar with this already. But so if we had, say, 0.1 on our equation was kind of like to the 10. Okay, then we have something that was 0.000000000, many noughts, and you'd forget how many noughts there were, you'd write it down wrong, and then if it was important for the thing you were making or the science you were doing, then you'd have some horrible disaster. So rather than write out lots of zeros, or write out lots of zeros the other way, if you were doing like 1 million, you'd write out 6 zeros. We have this format here where we have a number and then times by 10 to the power of something. Okay, and that allows us to write down numbers without all of these tedious zeros and stuff like that, which is quite useful because we can manipulate these powers of 10 using these exponent rules very easily. So if we wanted to know, for instance, how many diatoms there were in the bit of how many diatoms we'd need to cover kind of the ocean. Okay, so these are a small bit of marine plankton. We could very easily divide the area of the ocean. I guess that's not the area of the ocean, but we could by this very small number without worrying about all these zeros. We just use the exponents. So the way, and yeah, it's really important in earth sciences. I guess slightly less important than in physics, but we do look on very big scales and very small scales. Okay, so the size of planets to the size of atoms. So we have a huge range of sizes. There's this term orders of magnitude. Okay, so what that refers to is this number here, the exponent. Okay, so there's 1 order of magnitude difference between the size of the Earth and the size of a hurricane. Very topical this week. But there's 10 orders of magnitude in between the size of a diatom and the size of a hurricane. So that's a term you might hear quite a lot in terms of orders of magnitude, as in your answer was wrong by 12 orders of magnitude would be a horrible thing to say to students, but probably factually accurate. So again, the general form is you have some number, and the number at the front is between 10 and 1. And the number of digits in that number, it's like 8.73942, something like that, is very important, because that tells you how accurately you know that number. Okay? And then you have some coefficient, which is times b, which is usually 10, because we have 10, we like to count in base 10, we have 10 fingers. Some societies used to have base 12, because they counted on their knuckles. And then E is the exponent, so that's the power or the order of magnitude. Coefficient, B, base number, that's what I said that the wrong way around, but yeah, we go. So yes, for example, the age of the Earth, 4.543 times 10 to the 9 years, is much better than writing out 4543000, how many zeros I've lost count already, to get the age, right? This tells me that I know that the age of Earth is a bit of the order of 1 billion years old. 10 to the 9 is 1 billion, 10 to the 6 is 1 million. So it's quite helpful for just quickly getting an idea of how big something is using this thing. It's very important here that we've got basically 4 significant figures. So that tells us the precision till we know the age of the Earth. If we knew it more accurately, we would have another digit after that. If we knew it less accurately, we would have fewer. Not less, fewer. So here are some examples of things. Now I'll just get on to, so quite often we have these prefixes in front of things, sort of like kilo, mega, giga, peta, all those things, tera, for usually these things are prefixes comes in orders of magnitude in jumps of 3. So a kilogram is 1,000 or 10 to the 3 bigger than a gram. A megagram is 10 to the 6. A gigagram is 10 to the 9 grams. But they're not all. So some we have decimeters and centimeters. It's generally good practice to stick within the SI unit. So annoyingly, kilograms is the SI unit. So rather than start off with grams, we say how many kilograms is our base for our thingies. So for instance, with meters, we might, rather than say how many centimeters something is, we would say how many meters, and then use the scientific notation. Okay? So engineers don't do that. They use millimeters, and it's all a painful way of getting things wrong. So before we break for next week, I just want to make sure that you know how this stuff works on your calculator. Because how it works on your calculator, and how it works written down, and how it works on Excel are all annoyingly different. And how your specific calculator does scientific notation may be different from someone else's. So what you should do is make sure that you know how your calculator works and take that calculator to all of your exams. Okay? If you lose your calculator, make sure you buy one of the same type before the exam so that you know how to navigate it. So 3 times 10 to the 3, okay? So that's 3,000 in old money. You can write that in your calculator, maybe by pressing 3 and then maybe EXP button on your calculator, or you might have a times 10 to the 3 button on your calculator, okay? And then you would press the exponent. Okay? If it's a negative exponent, you wouldn't, there should be, if I wanted to do 3 times 10 to the minus 3, okay, there should be a button on your calculator that's not the minus button. Okay? So that's the button you would press for that. If you were doing it in Excel, okay, if I was to type this into Excel, I would write 3, then I would, the letter E, and then 3.
Is that a natural number?
Yes, it is, but in Excel, E means times 10 to the power of something. So in maths, E is a specific number, like pi or I or something like that. But in Excel, it's times 10 to the power of, and then whatever comes next. So if I wanted to type 1,000,000 into Excel, I would just do 1E6. Okay? Did you have a...
Yeah, I was just wondering, how often do we have to use Excel for math?
So you'll have to use it in some of the practicals. So I think particularly next, I don't think that the first one, not so much, the next one, not at all. You'll have to use it in some of your other courses. What degree are you on?
In geology.
So you'll have to use it in ELE. Actually, so Massimo said, oh, we're not going to help you with Excel, right? So I've added to learn a link to lynda.com. Have you heard of that? Lynda.com. So basically a company that makes videos and online learning things. And the university has paid for you to have access to that. So if you want to learn how to be an accountant or something, then you can use lynda.com. So I've put a link to their how to use Excel thingy. So if you don't know how to use Excel at all, never used it, then have a look at that. Or the demonstrators should be able to give you some help. And those of you who are doing Evolution of the Living Earth will have to do loads of Excel, but starting in week 6. So that's probably what she's doing. Okay? Right, so I'll see you guys next week. Let me